Record now. So for today, we are going to talk about the statistical testing and modeling. And it's going to be kind of different than the previous lectures because I will just go over some topics and then we will move to R, and sometimes we will go back to that slides in here. And so today, first of all, I want to talk about some statistical testing and modeling. And we will see some sampling distributions, and we will just check out the distribution for a sample mean for different cases. One of them is the standard deviation is known and the other one is unknown. And we will see some confidence interval. And at the end, we will see some hypothesis testing for one sample t-test and maybe for two means in here, okay? And this is what we are going to cover for today. And here is the first one. We will see some sampling distributions. I guess you are kind of familiar with this topic. And let's remember what was that. And it's just like any other probability distribution. But it is specifically associated with a random variable, and which is a sample statistic in here, okay? And so any statistic estimated from a sample can be treated as a random variable, okay? With the estimated value itself as the realization of that random variable. And so what was the central balance point of a sampling distribution? What is that? What is the central balance point of a sampling distribution? Do you have any idea in here?
Is it the median?
Yes.
Huh?
Median.
Actually, median works too, but generally we say it is mean, okay?
But mean can be to the left or to the right. So it's not a real balance. Actually, yes. Okay. Okay. It works.
Yeah, it's kind of a balance point. Random is not wrong, but still we will talk about the mean for today at least, okay? And maybe you remember that in previous lectures, we assume we knew the parameters of relevant example distributions in there. But in practice, these kind of quantities are often unknown. And in these cases, you may want to estimate the quantities from a sample, like estimate the mean from a sample. So it is therefore entirely possible that different samples from the same population will provide a different value for the same statistic. Realization of that random variables, and they are subject to variability in here, okay? So we know which is the central balance point of sampling distribution. It can be mean, and also like any other probability distribution, and the standard in here, let's say the standard deviation of a sampling distribution is referred to as a what? Do you remember what was that? The standard deviation of a sampling distribution is referred to what?
Oh, hi there.
What was that?
Hello.
Yep.
Hi there. It's me.
I am. So do you know the standard deviation? Any of you? I'm not asking just to you. I'm asking to all of you guys. Do you know what was the refer for standard deviation of a sampling distribution?
Do you mean the notation?
No, I mean it's standard error in here. Okay. It's refer, maybe you know standard error, but we are going to say standard deviation if we are talking about the sampling distribution in here. Okay.
Okay.
So this slight difference in terminology, the change in this terminology will be reflecting the fact that the probabilities of interest are no longer tied to raw measurements or observations, but rather to a quantity calculated from a sample of such observations in here, okay? And the theoretical formulations for these formulas for various sampling distributions, therefore, depend on the original probable distributions that are assumed to have generated the raw data and the size of the sample itself. Okay? So it is important for us, the sampling distribution and also the size of your data, which are really important in here. So, if you are looking for the distribution for a sample mean, if you don't know the standard deviation in here, let's say, so when the true value of the standard deviation, which is sigma x, is known, then the following are true, okay? Here is my standard deviation. So in this case, you are assuming that you know standard deviation in here, the true value of the standard deviation. Okie dokie. So do you remember anything about this one? You want to say something? So if x itself is normal, the sampling distribution of x bar is a normal distribution with mean, mu x, and standard error, sigma x over square n, okay? So here is what we can say about the distribution of our x bar. If x is not normal, the sampling distribution of x bar is still approximately normal distribution with mean mu x and standard error, and this approximation improves arbitrarily as n goes to infinity. Okay?
Okay.
So do you remember what we were calling this one? This guy?
Central limit theorem.
Yes, we call that the central limit theorem in here, okay? If your x random variable is not normal, or you are not sure if it is normal or not, the sampling distribution of the x bar related to the x still has normal distribution with mean mu x and the standard error sigma x over square n, okay? So, in our following code, when we move to R, we are going to use this information a lot, okay? And so, for the second case, if your distribution, you are looking for the distribution for a sample mean, but you don't know what is the standard deviation, okay? So you commonly won't know actually the true value of deviation of the raw measurement distribution, which is generated from your sample data, okay? In this, what you will do is that you will replace your sigma x, maybe we used before, that standard deviation in here, our sigma x we used. We can use it if we know that, but if you don't know what is sigma x, so we are replacing that with sx, which is the standard deviation of the sampled data, okay? So Sx is the standard deviation for your sampling data in here, okay?
Okay.
So this substitution introduces additional variability that affects the distribution associated with the sample mean random error in here, okay? And the standardized values of the sampling distribution of x bar is going to follow a t distribution. I guess you should be familiar with this concept, with these new degrees of freedom. And standardization is performed using the standard error in here. If n is small, then it is necessary to assume the distribution of x is normal for the validity of this t-based sampling distribution of x bar. So we said something in here, and we want to talk about them now. We will move to R in a minute, but I want to give you an example to practice what we have taught so far. Okay? Are you guys there?
Yes.
Yeah, we're here, Professor. I just think it's
Yes.
because this is a lecture style part that everyone's being silent because they're expecting you to say something more. That's why I don't think I think we're all still here.
So you are all here, but because of the
We are listening.
you are
Yeah,
just
exactly.
listening. Okay. Okay. So I'm going to give you an example, and please try to get the idea what's happening in this example, and we are going to move to practice this one, okay? Move to R to practice this one, or R studio. So please suppose the daily maximum temperature in the month of January in Antalya follows a normal distribution with a mean of 22 degrees Celsius and a standard deviation of 1.5 degrees, okay? Then, in line with the comments for standard deviation known situation, for samples of size n equals 5, the sampling distribution of x bar will be normal with mean 22 and standard error of almost 0.671. Okay? So, now we are going to generate or have some row distributions along with the sampling distribution in here and try to get the idea what is going to happen in here, okay? First of all, let's move to R Studio. Maybe you want to open it with me. And here is my R Studio. And now we are going to generate some raw data and see what can we do with that one. So here is my X values. And I want to generate a vector of some sequence. 16.
Sir, can you please try to make the font a bit bigger? Because I think it's a bit smaller than like last time.
Oh, sure.
Okay, that's great. Thank you.
Better?
Yes, definitely.
Okay, perfect. Maybe I can just stop share and just share my R Studio. Then it's going to be much better, I guess. How is that?
This
Okay,
is
this is
good.
definitely better.
Perfect. So let me just adjust here. So we are going to generate some X values in here, 16 to 28, by let's say 0.1, okay? So here are my X values. I have that vector, I generated a vector. And so being a probability density function, the d-norm function itself doesn't provide probabilities, okay? We have some functions, like say d-norm. Maybe you know r-norm to generate some random variables from a normal distribution, okay? This time we are going to use d-norm function in R, and this is so the normal, we have this normal distribution, and this is the distribution function, I mean the density distribution function, quantile function, and random generation for the normal distribution. So the first one is the density, okay? So d-norm function itself doesn't provide probabilities, okay? Merely the values of the desired normal function curve fx at any x. So if you want to plot a normal density in here, you will therefore be able to use sequence to create a fine sequence of values of x's, and you are going to evaluate the density at these values with d-norm, okay? Please get the idea. First, we have x values, and then we will get fx values depending on these x values by using d-norm, okay? And then we are going to plot them. So for example, to produce an image of the standard normal distribution curve, we will generate a code and with these x values getting from d-norm. And this d-norm, which includes specification of your mu and sigma, and it's going to produce the precise values of fx in here, okay? Let's say what I'm talking about. I have my dnorm function. By using dnorm, I want to generate my fx depending on this sample. So here is my dnorm function. I am going to use my x values and we'll find the corresponding densities. And so mean is 22 and standard error is 1.5 over square root of 5. Maybe I said square until now. Yeah, it's going to be square root. And here is my densities now. It's the same length with x values, much smaller, you see them. So we have these samples now. So right now, I want to plot these values, okay? Let's say you want to plot your x values versus your fx values in here, okay? And let's say my type is going to be L. You can just play with these parameters in here. LTY equals 2 and LWD equals 2 and xlab, let's say my xlab is just blank and my ylab is just blank. So I have my plot now. This is my first plot I want to have, okay? Here is my first one. And in here, I want to add a line and from just going from 0, and let's say it's going to be gray. Here is my line on 0. And now I want to get my fx values from dnorm, which are x values and 22 and 1.5. You will see where we are going to use them. And now I want to add some lines with x values, with fx values, and LWD equals 2 now. Okay. Here is my normal curve from sampling distribution, and here is my normal curve from raw data. So let's just add a legend in here, and maybe it's going to be much clearer now. And in legend, I want to add it in top right. And so here is my legend. Let's just say the first one is my raw observation. Let's just make it bigger maybe in here. Sorry guys, let's make it bigger. Okie dokie. To have some area. The first one is going to be my raw observations distribution, and the second one is going to be sampling. Let's move it to, and here is my sampling distribution mean, and we want to add some more parameters in here. It was 1 and 2. And LWD was 2 and 2, and we have, I don't remember why I was adding this. So here is my plot. I'm going to have it one more time. So we have, in this example, we have two cases. We have the sampling distribution. Let's get it bigger maybe. So we have the sampling distribution, okay, X bar, which is clearly taller in here and skinnier normal distribution than the one tied to the observations. So this makes sense, of course. You expect less variability in an average of several measurements as opposed to the raw individual measurements in here. And also, the presence of n in the denominator of the standard error distance, the standard error, which is going to dictate a more precise distribution around the mean if you increase the sample size, okay? So if you have like bigger sample, then your distribution is going to shrink more, okay? So that means it's going to be very less between samples of a larger sizes in here.
Hocam rica etsem legend'la başlayan kodu atabilir misiniz?
Maybe I should just send all of them to you.
Okay, thank you.
You're welcome. So here is I send it from the chat. Okay. So now you can easily see what is the difference between the rows of observations, the real values in here, or the observation from sampling distribution, just with this example, okay? So do you also know this P norm? It's just the same place in our D norm in here. We have a P norm, and this is just giving the distribution function in here, which is the vector of probabilities. So we will just check out for another example in here, okay? Let me so go back to this. And here is where we just, so I want you to find the probability X is smaller than 21.5, which is the probability that the sample mean will be less than 21.5 degrees based on a sample of 5 random days in January in here. Okay? No, which is not the sample mean, maybe. And this is the sample mean, actually. And this is the probability that a random chosen day in January and has a maximum, let's say, has a maximum temperature of less than 21.5 degrees, okay? So by using R and using this P norm, you can easily find Px is smaller than 21.5, which is the probability that a random chosen day in January has a maximum temperature of less than 21.5 degrees, okay? Can you just try to find it by using P norm in here, this one?
Yeah, sure.
Okay, thank you. So in here, Q is just vector of quantiles. Maybe you can just use 21.5 in there and just fill out the mean and standard deviation in here, okay? Please keep in mind that we are asking for X, not the X bar, okay? The next question is going to ask for X bar in there. So maybe you can send me the answer by chat. So Leka, please be careful. We are talking about the x, not the x bar. So you may not use standard error now. You can just use standard deviation. Okay. Did you get the idea?
I'm gonna send it in a tiny bit. Just give me a second.
Okay.
Did you mean this one?
This one, yep. Now it's correct because we are looking for let me remind you, the probability that a random chosen day in January has a maximum temperature of less than 21.5 degrees, okay?
Yeah, okay.
I only get one answer. Are you guys there working on that? It's really easy, guys.
Yeah, just give me a second.
Yeah, Begum, it's true, I guess. And yep. Kibra, it's true. But I think you did it together.
No.
So we can just use P norm and just add the 21.5 as this Q in here. Okay, it's just your quantile in here. And you will just put mean and standard deviation in there.
Can I ask something?
Yep.
So if we wanted to find the probability of x bigger than or equal to, we would put just simply 1 minus, right?
Yep. Yep.
So P norm will always calculate the probability of less than. Okay.
Yes, Ahmed, that's true. So I will continue, I guess. I will continue in here. Let me stop share and just share my RStudio with you guys. And then let's just keep it bigger. And now we are looking for what? The P norm. And our quantile in here is just 21.5. And the mean is what?
22.
22. And our standard deviation in here is 1.5, okay? And now this is just the probability that a random chosen day in January has a maximum temperature of less than 21.5 degrees is just 0.27, okay? And if you want to see different than this one, let's say, if you want to see in here, find the probability that the sample mean will be less than 21.5 degrees based on a sample of 5 random days in January. So this time, you will just use the same guy in here.
But the standard deviation will be different.
Yes, but the standard deviation is going to be different. Instead of 1.5, it's going to be 1.5 over square root 5. Yes, perfect. Then now it's kind of smaller, okay? So maybe we want to see these two probabilities on this graph in here. Let's say, let's go back to RStudio. And we want to just, let's go back our plot. We want to just add this guy, these two areas in here, and to see these two probabilities on the plot, okay? So we will use the same guy, the previous one in here. Let me just use the same guy. And now I want to add some some lines in here. Let's first have the graph. We have the same graph. And now let's use this one. And now we are going to add some line on vertical 21.5, which is, this is coming from the question. And let's say our color is going to be gray in here. So we have that line. Maybe now you see 21.5 line on the graph this time. And now we want to add some, we want to get the x values, okay? And let's subsample of x values which are smaller than, and x values which are smaller than or equals to 21.5, okay? And of course, also we want to get this fx subsample, the corresponding values for fx. And this is going to be fx, and here is what? We are going to correspond the values which are smaller or equals to 21.5. Okie dokie. Now also we want to get the ones from fx.semp. We also have fx.semp. So we use fx. So we also have fx. Let's say this one is fx sub. We are just using these fx values, also fx values, fx semp values and fx values. We have two. One is coming from the sampling distribution. The other one is coming from the row distribution. And let's say I have my fx sub coming from fx, and also I have my fx sub this time. And now we want to use this guy and the same values corresponding to this guy in here. Okie dokie. So if you just use polygon function, we have this polygon function in R. This is going to supply custom vertices in order to draw or shade a polygon on your existing plot in here, okay? So I want to add a polygon in my plot. Let's say I will use some C-bind, and this is going to be 21.5. And for that one, I have x values sub. And for corresponding y values is going to be from 0 to fx.sub. And now let's density is 10. You see what I am doing in here? By using this raw data, I shaded the area smaller than 21.5, just using polygon in here, okay? And also I want to add another polygon to my graph in here by using almost the same, yeah?
I feel like it's tiny bit too quick. Like,
Yeah.
I'm having a bit of trouble, like, with the last part, I guess. I'm still writing it. And
Do you want me to wait for a while? Just
Yes.
more so, like, just take your time. It's fine, you know?
maybe I can just send you the code, then you don't have to write, okay?
Yeah, but in general, like, as well, I feel like I enjoy your classes a lot more when it's a tiny bit slower.
Sure.
But the class is still great. I'm not like...
I will do that. Let me just send you the last codes I used for the last graph. You can just use my code from chat, okay? Maybe I should send it to everyone.
Okay.
And here's what. So you can just take it and use it from there. In here, I'm going to just keep it, make it bigger maybe, okay? And now maybe in here and in here. Okie dokie. Here is my code and here is my plot in here. Okie dokie. So let's start from scratch. I have my plot. And this is coming from what? The sample or the raw data?
Sample.
This is the sample. And we are adding a 0 line just to see where it is. And we are generating densities from our raw data. And also we are adding the lines from what? The last one. Where is it coming from?
Wait,
Curve, the last curve, that one, I mean. Where is it coming from?
it's
Huh?
it's the mean distribution.
This is not the mean distribution. This
Oh,
is
sorry.
the distribution of raw data, okay?
Oh, okay.
This is the distribution of the raw data. If I add these legends and they're going to, maybe I can, if I say 1, 1, what is going to happen? Let's say. I didn't like it. Oh, right there. Okay. Now I want to add this ab line. Maybe you were remembering in that question, we were looking for the temperature smaller than 21.5. It's on x-axis. Now I want to get my x values just around here, okay? So I have two different distributions. First of all, I will just index these values, and then I'm going to choose the ones corresponding to that values on y-axis. And here is axis. Here is the one from raw data. Here is the one from the sampling distribution, okay? So I want to add the first polygon depending on the ones between my raw data and the line, the limit we added, and add another one, okay?
Okay.
Maybe by just changing, this, let's say, some properties in here. Let's say my density is 10, and I want to add some angle, and then it's going to be much better, I think. Just 2. So let's start over. And here is my second polygon, okay? I just shaded this area too. Now we are able to see all of them. I can just send you the last line of the code I added so far.
Okay.
And, oh, sorry guys, okay. So now we are able to see the shaded area and everything on the line. So by using this polygon function, you are going to add some custom vertices in order to draw or shade your plot in here. And so shading lines we implemented them by using the argument density, number of lines per inch, and angle. This is going to be slope of lines in degrees. This default is 25 in there, but we play with that too. So, okay?
Yes.
Okay. So maybe you should keep in mind that to evaluate the probabilities in here, we know we have some knowledge of the parameters governing X, like mean values, standard deviations in here. So rarely in real life, you have these quantities, okay? Instead of that one, you obtain a sample of data and calculate summary statistics depending on that one. And we will talk about them after the break, okay?
Okay.
I want to give you some break, and let's say, and see you at 14:30.
Are you going to be here?
I'm planning to just go out for a while, then come back, okay?
Okay, like because I had a question, so I wanted to.
Okay, maybe when I come back.
Okay.
So now we are going to produce random numbers from normal distribution. And do you remember what was the function to generate random numbers from normal distribution? Do you remember that one?
R norm, I guess.
R norm.
R norm. And when we just write this R norm, you will just go to the same page, and it's just giving you the random generation for the normal distribution with mean and standard deviation you supply in here. So let's say our x is coming from a normal distribution for Antalya, and 22 and 1.5 normally distributed in here. So if you want to generate some random variables depending on this distribution, okay, we can just use, let's say I have my observations, and my observation is coming from a normal distribution. Let's say I want to get 5, and my mean is, sorry guys, my mean is 22 for Antalya, and the standard deviation is going to be, you can see that the default value is 1, which is standard normal distribution, but our distribution is different than the standard normal. These are my 5 random numbers. So the best guess of the true value of your mu x and sigma x is going to be x bar and s. And let's say you want to guess your observation mean. Sorry, guys. I want to guess my observation, and your best guess is the mean of your observations in here. Okay? And this is your x bar. Your x bar is 22.20. Okay? And your best guess for sigma x is going to be sx, which is, let's say I want to get my standard deviation, and this is going to be ST for my observations in here, okay? And here is my standard deviation, 0.84. And if you want to calculate the standard error in here, let's see, I want to guess observation line standard error, and this is going to be observation standard deviation over square root of the number of cases. And here is your best guess for standard error. This is okay.
Yeah.
And of course, we will get different results because we are just generating random numbers, and your random numbers is going to be different than mine, okay? And if you want to find the probability that the mean temperature in a sample of 5 days, of course, is less than 21.5 based on your calculated sample statistics in here, what we are doing is that, let's say I have my T4, and this is going to be 21.5 minus observation mean in here over observation mean SE. T4, okay, minus 1. And why is that? Let's see.
Again, what is T4?
I will tell you in a minute. And my T4 is, I want to see the mean temperature is less than 21.5 based on my calculated sample statistics, okay?
Yeah.
And this is kind of, maybe do you remember this one? Is it similar to what?
Standardization.
Standard, yeah.
What?
Standardization.
Yes, it's a standardization, but this standardization is kind of a T distribution. Maybe you remember?
Yes.
Yeah.
Okay.
Based on samples, not the global value.
Yes, we can say that this T4 is just the T distribution with 4 degrees of freedom in here, okay? And depending on this T value, we can just find the estimated probability, okay? The
Okay.
first one is my T4, and if you want to find the probability from that, you can just easily use PT in here. And my degrees of freedom is 4 for this question. And here is my probability in here. Okay?
Yeah.
You get the idea what's happening?
T is probability of T distribution.
Yes. And it's coming from my observations in here. Okay,
Yeah.
from normal distribution. But
I
this is
see.
the probability that the mean temperature in my sample is less than 21.5. Okay?
Honestly, this lecture is kind of like a summary of everything that happened after the first half of 155 and the first half of 156.
Okay, that's good.
Kind of.
And also maybe it's good to practice their meanings in R.
Yeah, it's true, definitely.
Okay, okay. So now you want to plot this T distribution with 4 degrees of freedom, okay? And we will mark off these probabilities. And we will also have these densities from standard normal distribution, okay? And to see if we can compare them. Okay, guys?
Can you please repeat it?
So I want to plot this T distribution with 4 degrees of freedom. And we will mark these probabilities on the plot, similar to the previous one. And also we will get this density from standard normal distribution, okay? Standard normal distribution means that you have 0 as mean and 1 as standard deviation. And so this is going to be the standard version of normal distribution with 22 mean and 1.5 over square root 5 sampling distribution from the earlier, okay? I think it's going to be much clearer when we have the plots together. Okay, guys?
Yeah.
Okay.
Sure. Let's see what I'm talking about. X walls. Let's generate some X values together. Let's give some arbitrary sequence in here, -5 to 5, and let's say my length is going to be 100. It depends. You can just choose whatever you want. So I have 100 values now. So for these densities, I can use dt. Okay, here is dt. I can just get the density from standard T distribution. Okay, very similar to d norm. Okay, instead of d norm, right now we want to use dt to generate densities in here. Let's say I have my fx. I'm just finding the fx values, the function of the corresponding values of my x values. Let's say fx sample t, because it's coming from T distribution. And can you see now, guys? It's okay. The font is okay?
Yeah, everything is great.
Okay. So we have dt. I'm going to use x values. Okay. From these values, depending on the degrees of freedom as 4, you have these fx values for your t. So right now, I want to plot them. Let's say I have my x values, the sequence I generated at the very beginning, and I want to have some normal distributed data, like a standard normal with these values. Okay, just give some parameters in here. I want to have line LTY is 2. You can just play with them. LVW is 2, and color is gray, and gray. And now let's say my x limits are -4 to 4, and also I don't want to add any x lab, just blank or y lab. It's going to be black. This is going to be my first plot I want to add now. Okay, guys. And depending on my normal distribution. Here is the first one, okay? And now I want to add some lines of my t distribution. Let's add some lines. Where was that? I have my x values, and also I generated these y values, which are t. Okay, this is my function values. And let's choose different LTY parameters and LDW. So I added the lines in here. Maybe you see that. This guy is coming from my t distribution. So maybe I want to just mark up the ones which are smaller than, what was that? The T4 in that probability in here. Okay, guys. So I can just use polygon again. Here is my polygon. And I want to see bind what. Let me just copy and paste this part, which is going to be much easier for all of us. Here is my polygon. And now I'm going to use T4 that we found before. Maybe you remember, it was on that x-axis. And we have x values smaller than that. And also we have same fx values corresponding to these. That means we are going to find y values too. Okay. Here is my polygon. I want to add the ones which are smaller than that. Let's say, let me just add everything to your chats and then, sorry guys. Here is what.
Professor, this is a bit of a random question, but what's your favorite graph?
I mean the function to get plot.
No, just like the looking graph. Which one do you think looks the prettiest?
Actually, I like ggplots mostly, and line graphs with ggplot. Or sometimes I like maps in there, but when we are talking about these descriptives, I think I would use deadlines if it is possible. You know, because sometimes depending on the type of your data, and you have to use some of them. For example, if you have some categorical data and also your numeric data, then maybe box plots will be much better to show them. Okay.
Yeah, that's true. I mean, I was looking at some graphs yesterday after we had a midterm yesterday. And the Monte Carlo one looks so cool. It's like 100 lines. It looks so advanced, you know.
Yeah.
That's why I was like, I thought about it the second. Sorry, it's a bit of a random question though.
No, it's okay, no problem. So we just added the shaded line in here, okay? And now we can just add some legend to see which one is which. Let me just make it greater. And so let me add it to your chat. And you can just use this legend too. So in here for the gray line, this is the density of normal distribution. And that guy is your t distribution with 4 degrees of freedom. Okay, they're kind of similar, but it's kind of, maybe you notice that t distribution is heavy tailed. Can you see how it is? Tails are heavy. You see that?
Yes.
Yeah.
Generally, when you have two distributions, one is like with similar parameters, and when you just have their distributions on the map, you will see that T has more heavy tails. That means T is more robust than normal distribution. Okay, this small difference between normal distribution And t-distribution sometimes makes a bigger impact on your analysis in here. Okay, guys, do you have any questions, comments so far before moving?
I think the second part of the lecture is a lot better than the first part. Like the energy is calmer. Like I felt like I understood a lot more.
Okay. Okay, perfect. Maybe this is the style of lecture you are getting accustomed to that for today. I don't know.
I really wonder how the lessons would have been if we were in the school.
So let me first get the question, and we are going to talk about the confidence interval for the rest of this lecture for today. And let's see what we are talking about. And so when we are talking about the confidence interval, it's an interval defined by a lower limit and upper limits, okay? So we use them to describe the possible values of a corresponding true population parameter in light of observed sample data, which is important for us. So the interpretation of a confidence interval therefore allows you to state a level of confidence that a true parameter of interest falls between these upper and lower limits. And they are often expressed as percentages in here. For symmetric distributions, like normal distribution, like t-distributions in here, and the general formulation is like this guy. You have statistics plus minus your critical value and standard error times standard error. Statistics is the sample statistics under your scrutiny in here. And your critical value is a value from the standards version of the sampling distribution, and that corresponds to alpha. And maybe you remember that we generally get alpha as 0.05, but it's depending on your experiments in here. And the standard error is the standard deviation of the sampling distribution. Okay?
Okay.
Yes.
So this is what we are talking about. And let's see, we want to check for an interval for our mean in here. Suppose you know the observations are normal distributions, but you don't know the true mean, which is mu x, which is set at 22, or the true standard deviation, which is sigma x, which was 1.5 before. So set it up in the same way as earlier. Assume you have made some observations here. So we will move to RStudio again, and let me just share my screen with you guys, okay? And let's say, where is my screen share? I want to share my RStudio with you guys. In here, we are going to generate a sample with 5 observations, okay? And here is my, sorry guys, I did something wrong. So here is my confidence interval title. So I want to get a sample from a normal distribution. Here is my R norm function, and n is 5, and my mean is 22, similar to the previous example in here. And my standard deviation is going to be 1.5. Okay. So I want to generate 5 observations. Yours is going to be different than mine, around 22. Okay. So we can just find the sample mean, x bar, and the sample standard deviation, which is S, and the appropriate standard error of the sample mean, which is S over square root n. So if you want to get the mean in here, which is my, and I want to have my temporary mean, or temperature mean, sorry guys, or whatever you call it. And here is coming from my sample, okay? now I'm able to find my mean value, which is 21.94. Okay. So also you can always find the standard deviation of your data. Are you guys there?
Yes.
Okay.
Yes, we're here.
Okay, thank you. I have a chat. What's that? Yes. Okay. Some people are writing on chat. And we have this temp.st. I hope. We have that. If you want to find the standard error, please remember to use the square root 5. So now you have in your, maybe in your global environment, you see that you have your ST, SE, mean, all of them. So let's say in here your aim is to construct a 95 confidence interval for your true unknown mean mu x. Okay, so given the fact that you know the row observations are normal and you are using S in here, the appropriate distribution is going to be your T distribution because we are talking about the sample. And since we have 5 observations, our standard, our degrees of freedom is going to be 4. So now we are going to talk about T distribution with 4 degrees of freedom. Okay. So for a central area of 0.95 under the curve, okay, alpha over 2 must be in either tail. Maybe I should draw this for you. Can you see can you see this now?
I think it will be better if you just stop sharing the screen to be able to see your video bigger.
Stop share and let's see. Can you see that now?
Yes.
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 So we have something like this. This is our distribution in here. And when we are talking about the critical values, if your alpha is 0.05, I hope you can see.
Yeah.
We can see it pretty well.
This is what? Alpha over 2.
Yes.
Yes. These are my critical areas, okay? And this is also alpha over 2, 0.025. And when we are talking about the 2 tails, you see that when alpha is this one. And please keep in mind that R is giving this area, okay? Which is 0.975 for our alpha. Please keep in mind that R is giving that area. Okay?
Okay.
Okay.
Let me show you what I am talking about. Let me show you. Okie dokie. So in here, let me share my R with you guys again. So R is giving this area 1 minus 0.05 over 2. 0.975. Okay, this is the area we are talking about. So this function, the R function we are going to use is based on a total lower tail area that I showed you before, and the total lower area from the critical value. Okay. So if you want to check out for this critical value in here, let's give it a name. Let's say it's a critical value. And if you want to check out for the value on here, you can use QT. And QT, and here is your probability. and our degrees of freedom is 4, and my critical value is 2.77, which is the value on the x-axis, okay? The positive critical value in here. So please remember what we were doing for our confidence interval before. We talk about it, I guess.
QT?
Excuse me?
What was QT?
QT is giving the critical value in here for T distribution. Maybe you remember that by using QT, we can find the quantile function. But in this quantile function, please keep in mind that R is going to give you a total lower tail area from the positive critical value in here. Okay?
Yeah, and if we write lower tail to false, it will give us the right area, right?
If you just write the lower tail, the -1, then it's going to be the left side on the graphic. Okay? So I mean, let's say you are on this plot, and if you are somewhere like that, and R is giving you this area, but if you are somewhere like that, if R is giving you to this area, always the left part.
But there is a
tail.
parameter, called lower tail, which is the default value has a true value. But if we write it to false, I think it will give us the area on the right, right?
Yeah, of course. If you are looking for something else, you can always play with the functions in R, okay?
Yes.
Of course, if you have something else in there, you should use that. But for this example, we are looking for this critical value to generate our confidence interval, the 95% confidence interval for the true mean mu x in here, okay?
Okay.
So we find the critical value on our plot in somewhere. This is just, and now I want to write my confidence interval for you guys. The first one is going to be, I'm going to have my mean minus my critical value. So I think I didn't run this part. Critical value times, and I will use standard error in here. And here is the first one. And the second one is going to be same with plus. And now here is the second one. Okay. So in here, you are 95% confident that the true mean maximum temperature in, let's say, Antalya in January lies somewhere between 20.40 and 23.48 degrees Celsius for this example. Okay.
Yeah.
So if you want to change the confidence or to add some more, or if you want to find the confidence intervals in a different way, let's say you want to find all of them at the same time, I mean 2 of them at the same time, you can just add like -1 +1. And here is my critical value for T. And my P is, let's say, 0.9 this time, okay? And my degrees of freedom is 4. And of course, I have to add my SE, standard error, in here. You can just play with this P, guys, okay? And here is my new confidence interval in here, or I can just make it bigger by giving different ones. And now for this one, I have different confidence interval. So you are always able to alter the intervals to change the confidence levels in here, okay?
Okay.
Any questions, comments? Did you get the idea of the confidence interval? But of course, there are several options or functions in R, and it's just providing some confidence intervals for you guys, okay? You can use them too.
Okay.
Perfect. So let me move to what? Let's see. I want to move to hypothesis testing with you guys. And now we are going to talk about this testing, hypothesis testing. And let's say we are starting with this one sample t-test together. And I want to start with an example in here, okay? So please suppose that there's a manufacturer of a snack and they are interested in the mean net weight of contents in an advertised 80-gram pack in here, okay? And they say that a consumer, and then a consumer calls in actually with a complaint, and over time they have bought and precisely weighed the contents of 44 randomly selected 80-gram packs from different stores and recorded the weights as follows. In that point, we should move to our studio and just get that vector together. And let's say, guys, let me give you that vector to you by chat. And here is our vector. Sorry to everyone. You can just get the snack vector in here. And here is my vector. I just copy it and paste. We are working on one sample t-test. Okay. Here is my snack vector. You see that they just weighted 44 contents of this randomly selected package, okay? Did you get the idea what's happening in here?
Yeah.
Okay.
Yes.
Okay. So let's see what is the claim of that consumer in here. I mean the customer in here. They are consumer, of course. And let's see what I'm talking about. And here is what? The customer claims that they have been short-changed because their data cannot have arisen from a distribution with mean mu equals 80. So the true mean weight must be less than 80. So you should investigate this claim, and the manufacturer is going to conduct a hypothesis test. They're going to use a significance levels of alpha equals 0.05 in here. And guys, you can see that these are our hypotheses, that we say that our mu is 80. And as an alternative hypothesis in here, this is a null hypothesis. And the alternative is that we are claiming that our mu is smaller than 80 in here, okay?
Yeah.
So if we want to move to this example in R, and let's say what we are going to do. First of all, I want to get the n, the length of this snacks vector, supposed to be 44. And I want to get the snack mean, or yeah, I want to get the snack mean, and which is mean of the vector. Here is my mean. Let's say what's that? 78.91 is the mean. And of course, to generate the test, we can get the snack standard deviation, which is ST function in here. We can just use it easily. And here is my vector. And when you just check out for your ST, you will see that it is 3.05. So we just write them, and we will see that when we just check out for this one in here, and here is what we are looking for: the given estimated standard deviation, which is the probability of observing a sample mean of 78.91 grams or less if the true mean is 80 grams in here, guys, okay? So the formal t-test statistics, you are going to test your hypothesis for a single mean with respect to your null value of mu0 is given here, this mu0 is coming from your null hypothesis in here, and here is your X bar you want to check for, okay?
Okay.
So now
Yeah.
let's see how we are going to do that in R. And now we will move to R again. And here is my R studio. We will just move to that part. And of course, we should find the standard error to use in our test in here. I have my snack SD. What should I do now, guys, to find the standard error?
The standard deviation over the square root of n.
Yes, thank you. And n is just n, that we already found that. And if you want to check for your standard error, it is 0.46 in here. So now we want to see how we can find our t value in here, which is, oh, sorry guys, which is something like this. I have snack and I want to find my t value. And now I will find something and do something in here. So first thing, I have my snack mean, and here is my 80, which is coming from the null hypothesis, and I will use my SE. And now here is my snack.t, which is -236. So you can use this value to check out. Also, you can just check for the test statistics and just to obtain your p-value. And if you want to do that, you can easily use pt, and it is going to give you the p-value corresponding to your t in here. And please try to give your degrees of freedom, which is going to be n-1. And so this is 0.01, okay? So, do we reject or not? When you just think about your alpha is 0.05 and the result p-value is 0.01. So, do we reject null hypothesis in here?
Yes.
Yeah.
Yes.
Because it is smaller than our alpha for this question. So, it says that if your null hypothesis were true, there would be only a little more than a 1% chance that you would observe the customer sample mean of X bar is 78.91 or less. And since this p-value is smaller than the predefined level of alpha, which was 0.05, and the manufacturer can conclude that there is sufficient evidence to reject the null hypothesis in favor of the alternative in here. So this is going to suggest that the true value of mu is in fact less than 80 grams. Okay?
We could also use the confidence intervals, right?
Yes, let's say we want to use also confidence interval, and here we have snack mean plus, we were using -1 + 1 times our quantile coming from this QT coming from T distribution 975. Let's say our alpha is 0.05 and n-1 is our degrees of freedom, and we should say times snack.se. Okay, this is the statistics, this is the critical value, this is the standard error, and here is our confidence interval. So depending on this confidence interval, as Leka suggested, we can say that it is not including the value of 80, okay? And this is just mirroring the result of the hypothesis test at 0.05 level.
Yeah.
Okay. So also, guys, there is a t-test function in R. You can easily use there. Here is my t-test. I can use that one too, which is maybe much easier. You want to use it for your snacks data, and your mu is 80, and your alternative hypothesis is just less. Okay, We are just mimicking our question in here. So here is my t-test. Now I have my t-value. Here is my degrees of freedom. And here is the same p-value in here, 0.01. Okay?
This is so cool.
Yeah. So why did we do all of them?
Yeah.
No, it's much better to see the steps first than to see the easiest way, of course. Okay?
Yeah.
Everything is same, but only one thing is in here is different than what we have found before. Maybe you remember that. Here is our confidence interval. But when you check out for the output of your t-test, you will see that they have minus infinity. Okay?
Why?
So we, in this output, we have t-value, we have p-value reported, and we also get this 95% interval. But you see that one of the values is minus infinity, is not matching the interval we find before. So the manually calculated interval is in fact a two-sided interval. That means a bounded interval formed by using an error component. So then it's equal on both sides. But the CI, I mean the confidence interval in the t-test output takes instruction from the alternative argument, like this one. Since we write less in here, it just provided a one-sided confidence bound in here, okay? So for a lower tail test, it provides an upper bound on the statistics such that the entire lower tail area of the sampling distribution of interest, and as opposed to a central area as the traditional two-sided interval does. But you can always use the ones we used before, okay?
So
Because
if we type more, then it will give us the lower bound. So we can just combine these two and create the interval.
Yeah, also you can do that, but you can always use that part and then just use our confidence interval, because in generally we are not using a one-sided confidence interval. It's not that common. Generally we use both-sided, okay? Even our alternative test is one-sided in here.
Okay.
Okay. What else? You can always find this one with a test. Let's say I want to use the t-test, same one, and my mu is 80, and you can just write two-sided. Let me not delete this part, and I can just copy and paste. And in here, you can just do, and just for your two-sided interval, okay? You can use this one to test, but if you want to get two-sided confidence interval, you can use this guy just by adding, let's say I want to use my confidence interval. And now you are able to get them, okay?
Yeah.
R always has some solutions to anything.
Oh my God, is this a list? And it just, oh my God, it's so good.
Yeah, it's so easy. It is so easy to use. Okay. And now we know, so for today, now we know how to do and how to find some sampling distribution and distribution for a sample mean, I mean. And we had two scenarios in there. The first one is not so realistic because we know the standard deviation. And the second one is that we are trying to, we don't know standard deviation, and we are using the sample standard deviation in here. And now after today, we know how to find our confidence interval for a mean. And we move to hypothesis tested as a last step. And we learn how to do one sample t-test. Okay, for today, I think we did a lot.
Yeah.
Today
I think
was
so
a very
too.